Have you ever wondered how cool it would be to walk through walls? Well, it's possible in the quantum world through a phenomenon called quantum tunneling. But to understand this a little better, let's first talk about a different topic called quantum entanglement. Let's use an analogy to identical twins Anne and Elise. If we don't know the name of each twin, we can simply ask one twin her name and we'll automatically know the name of the other twin no matter how far apart the twins are, because the twins are, in a sense, entangled. However, this analogy doesn't truly represent what happens in the quantum world because the twins each have a predefined state that can automatically be determined by knowing the state of the other. In the quantum world, however, particles do not exist in defined states, but rather in a superposition of various states, meaning that since particles behave like waves, they can be found in several different places at the same time. This means that, according to the Heisenberg uncertainty principle, when this cord is spinning, we don't know whether it's heads or tails, and we're uncertain about the state that it's in, because it can occupy both states, until we stop the coin from spinning and observe its state. Similarly, when we roll two dice, we don't know the sum of the dice because we don't know what numbers on each dice until the dice stop rolling. This means that when we roll the dice, there's a certain probability of the dice summing up to each of the numbers on this probability curve. Similarly, quantum particles have a wave function that represents their probability of being found in each of their potential positions. And here is where we come back to quantum tunneling. If particles experience a barrier like a wall, their waves would typically reflect back. But waves don't always reflect back perfectly. So, if the barrier is thin enough, there's still a small chance that the wave function can pass through a barrier before ending, making it possible for particles to be on the opposite side or inside the barrier. Take this glass of water for example. When I press my fingers onto the glass, the photons from my fingers tunnel through the glass, enabling us to see my fingers from the inside. Though seemingly insignificant, quantum tunneling is responsible for radioactive decay, spontaneous DNA mutations, and much more.